Now that we talked about the executor service, and we also talked about the thread pool executor, let's go ahead and see how you can apply the executor service and a thread pool executor implementation to implement the PrimeCheckerapp in a more flexible and convenient way than we did with our executors interface example from before. So just a quick recap of what the PrimeCheckerapp does. It's an embarrassingly parallel app, which means that all the different tasks can run without any dependencies. It's also compute bound, which means that the prime checking doesn't require I/O. And in this particular variation, it's going to use the Java executor service to check whether n random numbers are prime. So once again, you can run the app on my website. And this example also is cool because it shows a more effective way and a more robust way of being able to handle runtime configuration changes in the Android platform. I think I've talked about this before. When you have a phone in landscape mode and you rotate it to be in portrait mode or vice versa, then the way Android works under the hood is it tears down the current activity and then creates a new one. And by using the executor service, we can actually have all the computations continue to run concurrently and asynchronously while a runtime configuration change is occurring. And it's all very graceful and robust and resilient and efficient. Another thing that this example will demonstrate is how to handle thread interruptions. So it's actually possible to click on the interrupt button, and that'll cause the program to shut down the threads in the thread pool. So let's see how we might implement this. This particular implementation, again, will use a fixed thread pool where we are pegging it to the number of cores that the Java execution environment knows about our underlying hardware platform. And then we have a user interface thread, or rather Android gives us a user interface thread that will generate random numbers that are then submitted to and processed by worker threads in this fixed size thread pool. Internally, out of the box, the new fixed thread pool method on the executors class, the executors utility class, will use an unbounded queue to avoid deadlock problems. We also define another thread. We have a second thread that runs, and this is going to run in the background, and it's going to wait for all the futures to complete as the operations are run in the pool of threads in the fixed-sized thread pool. So we use this background thread to ensure that the user interface thread doesn't block. And that's very important because in modern GUI platforms like Android and iPhone's iOS and Java FX or whatever thing you use to write GUI programs, the user interface thread typically can't block for any length of time because that makes the user interface non-responsive, which is bad. Last time we talked about this example, we had something called a Prime Runnable, which we submitted using execute to an instance of the Java executor interface. Now, because we're going to be using the executor service, we have something called PrimeCallable. And PrimeCallable defines the two-way means for asynchronously determining whether a number is prime. You can see here that PrimeCallable implements the callable interface and is parameterized with something called a PrimeResult. We'll look at that in a second. That's essentially what keeps track of the number we're checking to see its primality characteristic and the result that comes back from checking its primality characteristic. The constructor for PrimeCallable stores the prime number candidate in a field. So it just stashes it away to be processed in the background by a thread in the pool of threads. And that thread or a thread in the pool of threads in the fixed size worker pool will invoke the call method. And as you can see here, the call method is going to call the isPrime method, which we've looked at before, which does that brute force computation to see if a number is prime or not. And what it does is it returns a prime result that will indicate the original number and whether that number is prime. If it is, the value's 0. Otherwise, it's going to contain its smallest factor as the second parameter in the or second field in the PrimeResult object. So PrimeResult is basically just a little tuple that matches the prime number candidate with the results of checking the primality. And one of the nice things about using this two-way model is we no longer have any dependencies in our PrimeCallable class on any Androidisms or Android classes or Android features like the main activity. In contrast, if you go back and take a look at the executor implementation, the Prime Runnable class had a dependency on the main activity, which complicated various things. When the call method is invoked, it's going to be running in a thread in the worker thread pool. And this way we get the results back, and it keeps everything nice and clean because we have two-way semantics here. Here's the prime number calculation. This is very similar to what we had before. The main difference being that every time we go through this loop, we check to see if the thread has been interrupted or not. And so by checking to see if the thread's been interrupted, we can be responsive if somebody clicks the shutdown button. And someone asked a good question on the Piazza forum the other day. They said, what's the cancellation parameter passed into the lock method? What is that all about? The lock method for the spin lock. How would that ever get called? Well, the answer is when someone clicks the cancel button on our app's GUI, that will cause that method to become true. And then the spin lock will detect that it's been canceled and it'll shut down rapidly. Otherwise, it could take a long time to shut down. Now, the other thing we have here that is different from the previous example is we're going to have a list of futures to prime results. And this is actually going to be stored in the main activity. So we're going to have a list of futures that store the results of concurrently checking primality of count random numbers that are going to be spawned within a certain range. And we'll see how that works in a second. So this list of futures is initialized using a Java sequential stream, just for kicks, just to make it fun. So here's what this looks like. We use the random number class to generate a stream of long numbers, long values, up to count in size or count random numbers. And we make them be within the range of S max value minus count to S max value. And by doing that, we ensure that there'll be duplicates in that range. We then go ahead and use a stream intermediate operation called map to obj, which takes longs and converts them into PrimeCallable objects by passing in a behavior, which is a constructor reference for PrimeCallable. So this constructor reference converts each random number into the corresponding PrimeCallable. And then we turn around and we map each of those PrimeCallables, which stash away the prime numbers that were generated randomly. We use the map method, which will then submit each of these PrimeCallables for execution in the background by the pool of threads. So ExecutorService : submit is a method reference that map uses to go ahead and submit each of these PrimeCallables for execution. And what submit returns is a future that is a proxy that represents the pending results from that task when it finishes running. And the last thing we do here is we simply collect up that stream of futures into a list of futures to prime results. So this is using the wonderful magic of Java streams, which is just so powerful and so cool. And we're collecting everything up and stashing them away in a list of futures. Future runnable is going to be the task we pass to this second thread. It's going to run in the background and will be used to redeem all these futures when they complete. It'll get the results of those futures and print them out. So future runnable is a runnable, and it's going to contain a list of futures to these prime results. And it'll also have a reference back to the enclosing activity so we can use it to print the results. And then here's the constructor. The constructor simply stashes away the activity in the list of futures in its fields. And here's the run hook method. This run hook method is what's used when this second thread is run, and this runs off the main thread to avoid blocking the main thread. And what it's going to do is it's going to run, and for basically each of the futures that are in the M futures field, it's going to iterate through them, and it's going to go ahead and make a get call to wait for that future's value to become available after the computation completes in the background that decides whether it's a prime number or not. And what get's going to do is we're going to use a really cool mechanism we'll see in a second called exception laundering to be able to avoid the need to litter our code with ugly try-catch blocks. So this particular way of doing things is what's called the synchronous future processing model, because we're blocking synchronously waiting for each future to complete in turn. The rethrow supplier method is something that's coming out of a class called exception utils that I have in my utils directory. And this is what's called exception laundering. We're converting a checked exception, which is what get expects, to a runtime exception. And you can read more about how and why to do this in the link, the Stack Overflow article below. What rethrow supplier does is it gives us back a supplier, and therefore if we actually want to get the results back, we have to call the get method, because that will be used to actually get us back the results that came back from the future get method. So we get back a prime result, and then we go ahead and decide whether it was prime or not and print the right output. If you run the app, or if you go back and look at the screen, it'll show what the output looks like. And when we're all finished, we tell the main activity that we're done, so it can go ahead and basically wait for the next count request to come in. Now, the other thing we have here is we have a very helpful method called interrupt computations. And this is what gets called back when a user clicks on that little icon on the app screen. That's the X that says basically shut things down. It's the shutdown button, if you will, or the stop button. And what we do here is when the user presses the cancel button, then we're going to go ahead and tell the executor service to shut down now, because we want to get this over with as quickly as possible. And then we also interrupt that background thread that's processing all the futures, so that it will also know that it shut itself down as well. And then we wait up to essentially half a second. We wait up to 500 milliseconds for everything to reach a point of graceful shutdown. And then that will the activity will go back to waiting for the next request from a user. So we basically shut down the thread pool and use that as a way to stop everything from running. Something else I'll just mention briefly. This is a very clever technique you can use with Android. It's called retained state. And this will be used to preserve all the concurrent computations and let them continue running when an Android runtime configuration change occurs, which is that rotation from landscape to portrait or vice versa. And what we do is we stick all the concurrency related objects into this thing called retained state. And then we're going to basically use this to store things like the future runnable, store things like the thread that we start, and so on. And then when the phone rotates, there's some lifecycle hook methods that get called back automatically by the Android framework. And the onRetain non-configuration instance method can be used. It's called back by the framework when an activity, the main activity, is about to go away, and we use this to stash the retained state object. And then when the new activity is created, we go look up and see, was there any retained state? And if there was, we use that and restore it so that we don't have to recreate these threads. They can continue to run while the configuration is changing. So it's a very powerful and cool Androidism. So that's the end of our overview of how to apply the Java Executor Service to the PrimeChecker app. We've now got a more powerful PrimeChecker. And if you want to play around with this, you can go ahead, go to my GitHub repository and download the code and try it out on Android and see how it works.